Hi students, today we are going to solve one more problem in the nozzles. So let us look at the problem. Now the problem we are going to solve with the use of the purely with the use of the Mollier diagram, HS diagram. Okay, so let us see how to solve this problem using the Mollier diagram. So first read the given problem. A convergent divergent, it is a CD nozzle, so it's a convergent divergent nozzle is supplied with dry saturated steam at 11 bar. If the divergent portion of the nozzle is 6 cm long and the throat diameter is 8 mm, determine the semi-cone angle of the divergent part of the nozzle so that the steam may leave the nozzle at 0.4 bar. Neglect the effect of friction in the nozzle. So this is the problem. Let me once again read the problem so that you can note it down in your paper. A convergent divergent nozzle is supplied with dry saturated steam at 11 bar. If the divergent portion of the nozzle is 6 cm long and the throat diameter is 8 mm, determine the semi-cone angle of the divergent part of the nozzle so that the steam may leave the nozzle at 0.4 bar. So neglect the effect of friction in the nozzle. So this is what the problem. So let me explain what is the question about. So the inlet pressure and the outlet pressure are given, and now we have to find what is the semi-cone angle of the divergent portion. So this is the convergent divergent nozzle. So let me take, this is the inlet side, so where the steam is enter here. So let us take point number 1, so that is the section number 1, and so there is a convergent portion. So this is the minimum cross-sectional area, so that we call it as throat. So the throat diameter is also given, so it is given as 8 mm, and the steam is leaving at the exit, which is at the divergent portion, and we don't know what is the area or the diameter of the exit, and we are asked to find the angle, so that is the off cone angle. So if the cone angle is full cone angle, so we are asked to find only the off cone angle, and the length of the divergent portion is also given, it as 6 cm. So this is the length of the portion. So first let us write down the given data. So what are the given data here? The inlet conditions are dry saturated steam. So the steam condition is dry saturated at inlet with a pressure P1 is equal to, let us take 1 as the inlet portion. So P1 is equal to 11 bar, which is given in the problem, and it leaves the nozzle at 0.4 bar. So P2 is 0.4 bar. So we are not given the throat pressure. So the throat pressure we have to find it out, assuming that we are getting the maximum discharge, that is the flow is at critical pressure at throat condition, and the question is asked to find semi-cone angle. So what are the things we are going to do is, first step 1, we will going to find the diameter at the exit. So we have to calculate what is the exit diameter, and we have to minus the diameter of this throat diameter. So if you minus this exit diameter with this throat diameter, we will get the two portions of the extra diameter. So we want only the half of that one. So less diameter, of throat divided by 2, we will get the one part of the extra diameter. So using the length of the divergent portion, we have to calculate what is the cone angle using the tan theta. Okay, so let us assume that the flow is happening at critical pressure at throat, which is that, so Pt divided by P1. So the pressure ratio is at throat is, we have taken as, we have already seen this is a constant, it is 0.578. okay, so the critical pressure ratio is 0.5, so that we can calculate what is the throat pressure using this constant into this P1, so inlet pressure, so that we can calculate what is Pt. So we'll do the solution part. So solution, so first, as I already told, using the critical pressure ratio, first we have to find the P throat. So Pt divided by P1 is equal to 0.578. So which gives that Pt is equal to P1 into 0.578. So which is nothing but Pt is equal to 11. It is the inlet pressure into 0.578 gives 6.36 bar. So Pt is the throat pressure. So that is, we have to find out 6.35. So now we know all the three pressures. So P1 11 bar, it is already given. Pt we have calculated as 6.36 bar, and P2 exit pressure is also given in the problem, it is 0.4 bar. So all these three pressures are given. So now let us take the using the Mollier diagram. Now let us see how to we are going to take the reading from the HS diagram. So using the Mollier diagram, which is having the H value on the y-axis and the S value on the x-axis. Now, so this is the HS diagram, and we are having the pressure lines flowing like this. So let us find the 11 bar pressure line first, and this is the saturation line. So the inlet condition is at saturation, so 11 bar cuts the saturation line, will give the inlet condition of the nozzle. So this is point number 1, and so we know what is the throat pressure also. So it is 6.36 bar. So that is the throat pressure. So the expansion is under isentropic, that is a common S value. So we have to draw a downward line, a straight line. So this straight line will cut the 6.36 bar line, so that the intersection point is 2, and it further expands to the other pressure, that is 0.4 as the exit pressure. So the down line cuts at 3, so this point will give the exit point. So corresponding values of this 1, 2, 3 points. So this is the inlet point, this is the throat point, and this is the exit point. So corresponding values of these points are taken from the HS diagram. So we will see the corresponding H here for point number 1, that is the inlet condition. We will be having the H1 value indicated here, and for 2, draw a horizontal line, and we will get the throat H also from the Mollier diagram. Similarly for this 3 also, the point number 3, will be having the H2, the enthalpy at exit. We can get it from the Mollier diagram. So now let me give the example or how to find the values from the chart. Okay, so let us see the chart. So this is the Mollier diagram. So now we can see the line. Here it is given that it is the saturation line. So a line passing, it goes like this. So this is the saturation line. and the bottom, so at the bottom, that is in the x-axis, we are having the specific enthalpy in kilojoules per kg Kelvin. Similarly, at the y-axis, I am getting the specific enthalpy in kilojoules per kg. So this is the specific enthalpy axis. So the saturation line goes like this, and the pressure lines, you can see this is the constant pressure. So the pressure lines are going from downward to upward. So these are all the constant pressure lines. The values are given in this near the saturation line. So the pressure values are given in the saturation line. Okay. Similarly, what are the other things we can find it out? So we can see the dryness fraction lines also coming this way. So you can see the dryness fraction 0.9, this is 0.85, and this is 0.8. So like this, the dryness fraction lines also given here, and the specific volume, the constant specific volume lines also indicated as a dotted line. So here it is 5.0, 2.0, 1.0. The specific volume lines are coming from the bottom to top. So these are the specific volume. So here the temperature lines are also given in the superheated region, and here I am having the dryness fraction line going like this. So specific volume lines are going like this. So this is the saturation line. Okay, so now for the inlet condition, so which is at for this point, so this point, so it is 11 bar. Okay, so 11 bar at saturation line. So you can see the saturation line here, and you will get there is a 10 and 12 lines are there, the pressure lines in bar. So 10 and 12. So we have to take a in between line, assuming a line is going in between 10 and 12, so that is our point. So correspondingly to the left hand side, we can see the value, that is for this point, that is for 11 at saturation, I am getting, it is a second line below the 2800 kilojoules. So that is 2780. So let us take or assume an approximate value, or even if it is an accurate value, then we will get the closer results. Okay, so for this point, that is the first point between the 10 and 12, I am taking it 11. So this 11 I am getting 2780, because 2700 and 800 are given here. So the lines, two lines below this 2880 will give this 780. So 2780. So let us take the reading as H1, that is this point, yes, 2780 kilojoules per kg. Now the throat point. So at the throat, that is the second point. So the same line which cuts the 6.636 line. So we will take 6 bar line. Okay, so let us take you please take a scale, and from this point draw a straight line, and which cuts the 6 line. The 6 bar line is coming here. So the 10 point here also. So it is intersecting this one is the throat section. So corresponding the value we are getting, I am getting as a 650. So the specific enthalpy I am getting as 650. So let us note it down. The enthalpy at throat is 2650 kilojoules per kg, and corresponding that values also, that is the dryness fraction and specific volume values also can be noted by the lines which are following there. So for this point the dryness fraction lines are going, so I am taking it is 0.96. so dryness fraction lines are there. So at this point, the 6 and 11 point, I am getting it is between 0.2 and 0.5 line. So between 0.2 and 0.5 dotted line, so it nearly comes at 0.96. that is the dryness fraction. So here the dryness fractions are going like this. So I am getting 0.96 line passing through that point, the first point. So you can make points using a pencil mark. So the constant dryness line passing through that point will give the value. So I am getting 0.96 line passing through the throat point. And similarly the specific volume lines also we can see that. So corresponding value we have to note it down. So I have noted down xt, that is the throat dryness fraction as 0.96 and a specific volume 0.3. Similarly for the exist condition, that is 0.4 bar from the same down line I am getting the 3. So corresponding value will give the H2 value. So from the chart I am getting the H2 value as 2250 kilojoules per kg, and in that point I am having a dryness fraction of 0.82. so here it is 0.82, line is flowing through that point, and specific volume line is flowing at 4.0. so the specific volume line are flowing like this. So at 4 bar, so we have to take 0.4 bar. So here it is 0.4, you can see that here it is 0.4. so 0.4 line will give the end point, and this point and this point will give the corresponding H value and specific line, dryness fraction line. So everything you can note it from the table. So I have noted all the values from the Mollier diagram. So H1, H throat and H2 exit corresponding 11 bar, 6.36 bar and 4 bar. So throat dryness fraction, specific volume values are also noted. Similarly for the exit condition also, the dryness fraction and specific volume also have noted. So this is the concept. So H, S and pressure lines are there, and these are the 3 points. So for these 3 points corresponding H, X, V, all these are noted dryness fraction. Now we have to calculate what is the velocity. So only knowing velocity we have to calculate the mass flow rate. So using mass flow rate, there will get V diameter. So the velocity at throat, we know that formula, it is 2000 root of 2000 into h1 minus ht. So that is the throat velocity. So here h1 is we already known, h1 is known and ht also known. So substituting that, we will get a velocity of 509 meter per second. Similarly at exit, that is C2, so it is root of 2000 into h1 minus h2. So it is h1 and h2. So corresponding value is 1029 meter per second. So these are the velocity at throat and at exit. Okay, so using this velocity we are going to find the mass flow rate. Okay, so now the mass flow rate through throat. So we know that it is AT into CT divided by VT. So AT is the cross section area of the throat and CT is the velocity through throat, and small VT is the specific volume at throat. So all these things we have noted, and this is the mass flow through the throat. So area is pi d square by 4. So d is the throat diameter into Ct we have already calculated, it is 509 divided by, so Vt also we have already noted, it is 0.3 specific volume meter per kg, meter cube per kg. So substituting the values, you please calculate it. So d is given in mm, so we have to calculate, convert it into meter. So it is 10 and 8 into 10 power minus 3 square, so d square. So divided by 0.3 we will get 0.08 kg per second as the mass flow through throat. So now let us calculate the mass flow through the exit, that is exit diameter. So m2 is again, so using the same parameters, so a2 into c2 divided by v2. So a2 is the cross section area at the exit, c2 is the exit velocity, and v2 is the specific volume at exit. So using all the values we have taken from the Mollier diagram, I am substituting here. So here it is area is pi d square by 4. So here d is d2. So exit diameter square into C2 is, we have already find it out, 1029 divided by 4. So solving this, calculating this value, we have to get the d value. So we know that the mass balance is maintained through the flow. So we know that the mass flow is equal at all points, so that the mass flow through throat is equal to exit. So now let us write this is equal to the throat value. So pi d2 square by 4 into 1029 divided by 4. This is the mass flow at the exit. So that is equal to mass flow at throat. So we have calculated mass flow at throat is 0.08 kg per second. So solving this, so we have to get T2. So pi d square equal to this much. So D2 I am getting 0.0198 meter. So 0.0198 meter. So it's nothing but 19.8 mm. So D2, so exit diameter is I am getting as 19.8 mm. So and the throat diameter is given, it's already given 8 mm. So the difference is, so this is the final portion. So the diameter given at the throat is 8 mm. So we have calculated the exit diameter as 19.8 mm. So this minus this divided by 2 will get this portion, and we know what is the length. So if you take tan theta, so this opposite divided by adjacent side will get the tan theta value. So taking the inverse we will get the theta. So that is the step we are going to do next. So this tan theta is nothing but, so this diameter minus this diameter, so we will give the 2 times, so divided by 2. So 19.8 minus 8 divided by 2 will get this portion only, then divided by this 6 centimeter is given the length. So here it is 60. So this value divided by this value is tan theta. So tan theta is 19.8 minus 8 divided by 2 divided by total length is 60. So this is the tan theta value, it is 0.099. So taking the inverse of this theta, we are getting the value of angle. So tan theta for this much is 5.66. It is nothing but 5 degree 39 minutes 45 seconds. So this is the off cone angle, the value of off cone angle which is asked to find out. So in this problem we have calculated the values without using the steam table, directly from the Mollier charts. So this is the one method of solving the problem using Mollier charts. So we can get all the values directly from the Mollier chart. If you are able to calculate, get the values from that chart, you can find the answer for the given problem. Okay, thank you.